Okay, any question from the previous class? Do you have any question on that? We still in the linear programming topic. No? Okay. Well, let me summarize what we have learned. Okay, I'm going to turn off the video so that to set the bandwidth of the internet. Okay, we learned about linear programming, right? Linear programming where all the objective function and also constraints are linear functions. Okay. And we learn graphical method, right? For the graphical method, it was intuitive technique that, well, you just identify the feasible region, feasible set, and then from the feasible set, we identify the direction of the objective function, right? The gradient of objective function, and then we identify we can determine the maximum and minimum point, right? We try to go to the direction where the objective function develop. I mean, well, for example, for maximum, in case of maximization, we go on the direction there, well, where the objective function improve. Okay, and then, well, why we still keep our solution on the feasible region. For example, in this case, where the feasible region is defined by, yeah, this corner. Okay, any point in the feasible region, well, can be our solution. And then we go on the direction of the objective function. Here we have gradient of objective function. So a plane normal to the gradient, it's we call it an isoprophic, right? Isoprophic curve, isoprophic line. And then, well, we try to move further in order to maximize the objective function. So in this case, the last point, the last point which is in the feasible region is C, right? Okay. Or if you want to minimize it, you go in opposite way, this direction instead, yeah. And the solution would be here, right? Because this normal, yeah, we can move farthest to the minimum direction. And then from that idea, I show you 4 special case, right? We have case of no feasible solution where we don't have a feasible region. Okay. And the second case is unbounded optimal solution. In this case, we actually the feasible region exists, and also, well, we can, well, there's a solution, but the solution is not defined because we have unbounded, right? This direction. For example, if the gradient is in this way, we can move further this way, and we don't have a limit. We don't have bound on this direction. So you see that we can go to infinity, right? In order to get the maximum objective function. But of course, if you're going to minimize this direction, yeah, and of course we can find the minimum point here, right? And the next one is dual degeneracy. In case of dual degeneracy, the active constraint, the constraint which is defined the solution is normal to our gradient, the gradient of objective function. In that case, you see that the solution is not the point, but there are many points, many coordinates, right? There are many sets of solution which they have, well, they all have a equal objective function, okay, identical objective function value. So in that case, we have a number of solutions, okay, starting from this corner to this corner, right? And the next one is primal degeneracy, where, well, actually the number of constraints which are required to the number of constraints which is required to identify to determine the corner, it's actually equals to the number of dimension, right, of our dimension. However, in some case we have excess constraint. For example, this point, you see that this point is actually, well, it's an intersection of three conditions, three functions, not two, right? But we need only two. In that case, you see that the constraint, we have excess constraint, right? In this case, we call primal degeneracy. Okay. And while we develop algebraic solution techniques, right? The first one is the simplex method. For simplex methods, it's quite easy and intuitive, but it's limited because we need that, well, because we need to change, well, a specific form of the linear original LP, linear programming, because on the right hand side we need the positive values, and then, well, the relationship here must be less than or equal. You cannot have greater than or equal. Okay. Also, we cannot deal with equality constraint using this algorithm. Okay. So it's, while once we transform our original problem to this standard form, where we minimize the objective function and all the constraints are inequality, and on the right hand side are positive. And then, while for each constraint, each inequality constraint, we add slack variable. Okay. Okay, and then we write the tableau. Okay. X1, X2, slack variable, S1, S2, S3. Okay. And then at the time, we assume the basic variable. The number of basic variable must equal to the number of constraint we have. For example, in this case, it's S1, S2, S3, basic variable, and then, well, each iteration we make the, what's it, in the column of the basic variable, there must be only one, right? And the other coefficient must be 0. Okay, we transform it. Okay, any questions regarding the simplex method? Asan, you have any question on that? Asan Khan.
Yes, sir. Sir, why simplex method is, you said that is limited.
Pardon?
Sir, why simplex method is limited?
Well, because the limitation of the simplex method, right? You answer. Your question is the limitation of the simplex method?
Yes, sir.
Yeah, because, well, we cannot deal with equality constraint, and we cannot deal with the, well, greater or equal. Okay, so, well, using simplex method, well, single phase of simplex method, you need to, well, your problem must be lesser equal, okay, where the positive signs must be positive. Okay, just that.
Okay. Okay, sir. Okay.
And wow, using simplex method, I think wow, you can do it. And the next one, we move to two-phase of the simplex method to wow, because as I mentioned to you that we have limitation on the form of the linear programming, and in order to deal with equality constraint and also the inequality constraint having a greater or equal relationship, we need two phases of simplex method, right? So for wow, we divided the algorithm to two phases. The first phase is just wow, the objective of the first phase is to transform the problem into a form that can be solved by simplex method, something like that. For this one, for wow, two-phase algorithm, the first phase we treat all the equality constraint and also greater or equal sign. For any equality constraint, we plus E1, okay, plus extra variable. We call it E1, E2, something like that. For example, yeah, the first equality constraint we plus E1, and the second equality constraint we add E2. And of course, we define a new objective function as a W as a E1 plus E2. And then we, of course, we write the table again. But at the first phase, our objective is to eliminate the E1, E2 from the system, from our linear programming. Okay, so yeah. Once we can eliminate E1, E2, or total or sum of E1 and E2, then we can remove E1, E2 from our system, and we start the second phase, which is similar to the simplex method we have learned before. Okay, for example, this case, you see that the simplex method we learn cannot deal with it because of what? Because of this constraint? No, this constraint is okay. We can deal with it. Because of what? Because we have to transform this one to positive first, right? The right hand side. Once we transform this one to positive 18, so this relationship, this sign change to lesser or equal. Okay. But the problem is on this one, because once we change -4 to 4, positive 4, okay, this sign changed to what's it, greater or equal. You see that, greater or equal. So we need two-phase algorithm in this case. So if we have signs of greater or equal sign, we need slack variable and also excess variable. Okay, we subtract by S3 and we add E1, okay, to this one. Okay, and the objective of the first phase is just to minimize W. W is E1. Okay, so we set W as E1, so E1 minus W becomes 0, and then we set up the table again. You see that from this table, because now W is -4, we have to solve this problem first in order to eliminate E1, right? By driving W to be 0. Okay, so once we finish the first phase, you see that W is now, well, we drive E1 to W to be 0 already. So we can delete this line we can remove this line too. So we obtain this one, this table. And you see that from this table, you see that we can use simplex method now. Okay. This example, I think, well, last time I show you, I explained you this example already. I gave you the video and also the slide, so you can, yeah, read it later, you watch it later. Okay, so for this week, well, I will introduce you the concept of duality. But the concept of duality, you see that what we have, for example, consider this linear programming, the system. We have a11 x1 plus a12 x2 plus blah 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 to a1n xn greater or equal b1, right? And we have the second line of, yeah, second expression, a21 x1 plus a22 x2 plus blah blah to a2n xn greater or equal b2. Okay, and we also have other, well, expression. Okay, so well, for the objective function, we have c1 x1 plus c2 x2 plus blah 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 plus cn xn, yeah, equal f. Okay, so where xi, all xi's are positive. Okay, and this system, you know, we can transform it to this system. Okay, where we have a11 y1 instead a21 y2 plus blah 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 to a mn m1 ym lesser or equal c1. Okay, what are different from, yeah, this system and this system? You see that, well, on the right hand side we have b1 b2, it's vector of b1 b2 to bm, right? And the coefficient of the objective function is c1 c2 to cn. But the system, you see that we have on the right hand side of the constraint c1 to cn. Okay, and the objective function, no, the coefficient of objective function becomes b1 b2 to bm. Okay, where we to be maximized, and from the original problem is f to be minimized. Okay, this is the concept of duality. Well, for any system, okay, with this objective function, we minimize this one subject to this constraint, this set of constraint. Okay, we can transform it to this form where we maximize this objective function instead, and we have this set of constraint. Okay, and the solution, it's identical. I mean, well, it's analogous because they are duality of each other. So this is the concept of duality. For this system, we can transform it to this system. Okay, and we call it primal and dual. Okay, primal and duality. See, from that one, well, I compared side by side. For the primal problem, we minimize objective function f. Okay, where it is f, it's a summation of ci, and we have constraint set of, yeah, equality constraint or, yeah, inequality constraint, get or equal. And the duality of this primal problem becomes maximized of new function, new objective function, and this time the objective function is well, biyi. And you see that the number of desired variables in the primal problem is different from the number of discrete variable of the duality problem. Okay, because well, let's say the primum problem, we have number of a discrete variable is n, right? The number of discrete variable is n. But for the duality problem, the number of the discrete variables is m. Okay, and the number of the constraints also, well, different. We starting from m variable here, but here we have no m conditions, but for duality we have n conditions. Okay, so you see that the number of variable, this variable in primum problem is identical to the number of relationship, the number of constraint in the case of duality. Okay, and the number of constraint in the primum variable, it's identical to the number of discrete variable in the duality. Okay, for example, if we have this primum problem, maximize f, where f is 50 x1 plus 100 x2. Okay, and we have constraint of 2x1 plus x2 lesser or equal 1250, and 2x1 plus 5x2 lesser or equal 1000. And the third constraint is 2x1 plus 3x2 lesser or equal 900. And the last one, x2 lesser or equal 150. Okay, all x, all these variables are positive. Okay, we can transform this problem to the, well, using duality. And the duality of this original problem becomes, well, minimized. Okay, you see that the primum problem is maximized. But in this case, is, well, the duality is a minimization instead. And the objective function also different. You see that, well, you notice the coefficient of the objective function this time. Well, it's the right hand side of the constraint of original problem, of the primum problem. Okay, 1250 here, right? This is 1000, so we have 1000 here, 900 here, 900. Okay, 150, and then this is 150. Also for the constraint, for the constraint, we can, from the primum problem, we can transform to duality. Well, for the first line, the first constraint, how do we get this coefficient? 2 is from this one, 2, yeah, 2, this 2, right? 2 from this one, and this 2 from this one. Okay, from the first column, x1. Okay, in the duality, the first constraint becomes 2y1. Okay, extract from this, 2y2 extract from this, plus 2y3 extract from this. Okay, and the sign of relationship change to greater or equal. Okay, greater or equal, and 50, we obtain this 50, the right hand side of the constraint, from the coefficient of the original problem. Okay, and while for the second constraint, we extracted from 1y1, 5y2, 3y3, and 1y4. Okay, we don't have y4 here because the coefficient of primum problem is 0 here, right? So it becomes 0. But this one, the coefficient is 1, so we have y4 here. Okay, and greater or equal, the relationship says greater or equal. Okay, and the right hand side, well, we extract it from this, yeah, this coefficient. Okay, any questions? Kadim,
yeah,
you go with me, right?
Yes, bro. Yes. Why can't we solve this problem with a simplex method?
Pardon?
Can we solve this problem using simplex method?
Yes, you can do it, right?
Oh.
But you see that, well, once we change it to duality, we cannot solve using simplex method, right? Because it is greater than or equal, right? So you need two-phase algorithm, right?
Yes, Prof.
And what is the useful of duality? You see that if we start from the duality, the right hand side problem, you see that we need two-phase, right?
Yes, Prof.
Yeah, but actually we don't need that two-phase because well we can transform it using this duality, okay, theorem.
Okay.
Yeah, then well once we use duality, then we can solve it, right, using simplex
Okay.
method. Okay, so so let me conclude the characteristic, okay, the property of duality. So the dual of the dual is the primal, okay. All right, so we have primal, right? The dual of this primal become this, right? And if you change it back again, you obtain the primal, right? That means, well, the dual of the dual is the primal, okay? And if both primal and dual problems have feasible solution, both have optimal solution, okay? That means, well, if you have, well, for primal problem, if we can find the solution, it has feasible solution, okay? Minimum F becomes, well, maximum P. All right, so that means if you can solve the primal problem, you can solve the dual problem, well, then the minimum F becomes maximum P, okay? If either the primal or dual problem have an unbounded solution, the other becomes, the other problem is infeasible. What does it mean? It means that, well, if you look at the primal problem and you solve the primal problem and you found that the primal problem is the case of unbounded solution, okay? So if you convert it, if you make a dual problem, the dual problem will be infeasible, okay? Or if you start from the primal problem and you know that you solve it and then you identify that the primal problem is infeasible, that means, well, if you make a dual problem and you try to solve the dual problem, well, you will see that the dual problem becomes unbounded solution case. Okay, you can follow, right? Sagu?
Yes, sir. Got it.
Okay. Okay, so, well, look at our example. For example, we have maximized z, right? Which is 2x1 plus x2. And we have constraint of x1 lesser or equal 1, x2 lesser or equal 1. Okay, and we have x1, x2, which is greater than, yeah, which are positive, right? X1, both x1 and x2 are positive. We know that the solution is at 1, 1, okay? And this problem, you know, well, we can transform this problem using the duality, okay? The duality becomes, well, minimized because we maximize here. So the dual problem becomes minimized. And minimize of what? We minimize of Z prim, okay? Z prim. And Z prim is, well, 1 U1, 1 U2, okay? Let's say, well, the decision variable of the dual problem, it's U1, U2. Okay, and for the constraint, okay, because we have 1, 1 here, it becomes 1, 1 here, right? Just that. So 2, 1, okay? In this case, well, the solution becomes, well, U star, the minimum point is 2, 1, okay? Yeah, you can try it by yourself. Yeah. You can try to convert it by yourself using duality. For example, the other example is, yeah, we have maximized x1, x2, and we have constraint minus x1 plus x2 greater or equal 1, x1 minus x2 greater or equal 1, x1, x2 are positive, and we well, convert it to dual problem. well, instead of maximize, now we have minimize. Minimize u1, u2, yeah, from this coefficient. The right hand side of the constraint becomes coefficient in the dual problem. And what else? Yeah, the first constraint become -1, 1. Yeah, from this -1, 1, right? And the coefficient of the second constraint becomes 1 minus 1. Yeah, 1 minus 1, right? And the right hand side is a coefficient of the prime problem. So 1, 1. Okay, 1, 1 here. All right, so the other case, we have maximize of x1 plus x2, right? So the constraint is x1 minus x2 lesser or equal 1, okay? And x1 minus x2 greater or equal 2, okay? x1, x2 are positive. And, well, we use duality, becomes, well, minimize of u1 minus 2 u2, okay? 1, 2. And here we have u1 minus u2 greater or equal 1. And yeah, minus u1 plus u2 greater or equal 1. Okay. All right. So
Ajahn,
yes.
what happen if the number of variables are more than number of constraints?
The number of variables.
More than number of constraints.
Yeah, it's possible. No problem. So the number of this variable of the primum problem becomes the number of the constraint in the dual, okay, problem. And the number of constraints in the primum problem becomes the number of this variable in the dual. Okay, no problem. For example, in this case, you see that the number of constraints and number of this variable are not identical. See?
Yes.
In the primum problem, we have only 2 this variable, but we have 3 constraints, right? So in the dual problem, we have 3. No, 4. The number of constraints of primum problem is 4. Sorry. So in the dual problem, we have 4 decision variables and only 2 constraints. Okay, you see that number of decision variable in the primal is identical to the number of constraints in the dual. Okay, and the number of constraints in the primal is identical to the number of decision variable in the dual. Okay, good. Okay, so well, from the idea of duality, we can further expand the concept of the simplex method. Okay, we call it dual simplex method. This one is quite well useful. Yeah, because dual simplex method can deal of any type of linear programming problem with, well, you don't have a limitation anymore, because well, even you have a kind of equality, or the right hand side is lesser, positive, and the relationship is greater or equal, you can transform it using duality, right? So let me explain the concept of the dual simplex method. So while we don't have limitation on the right hand side anymore, remember that for simplex method we have limitation, right? On the right hand side, the right hand side must be positive, right? And the relationship must be lesser or equal. Okay, because if it's greater than or equal like this, we need two-phase method. Okay, but for dual simplex method, you just transform this one to the greater or equal to lesser or equal like this. Okay, for example, the first one, x1 is greater or equal to 2.5. You multiply both sides of the expression by -1. So it becomes minus x1 lesser or equal minus 2.5. And the second constraint, x2 is greater than or equal 6. It becomes minus x2 lesser or equal minus 6, right? And the third condition, 2x1 plus x2 is greater or equal 17. So transform to minus 2x1 minus x2 lesser or equal minus 17. And we have x1 plus x2 greater or equals 12. We shade it to minus x1 minus x2 lesser or equal minus 12. Okay, so again we add the, because we we have a lesser or equal here, we add the slack variable, okay, s1 to the first expression, the first constraint, and then for the second constraint we add s2, right? And the third constraint we add s3. Okay, the fourth constraint we add s4. Okay, so transform to this. And for the objective function, well, we have 12x1 plus 16x2. Okay, so f, of course, f it's 20x1 plus 16x2. So yeah, we rearrange it. Okay, so then we add them to the table. Okay, the table is very similar to simplex method. Yeah. We put the coefficient of each variable. Okay, we have x1, x2, s1, s2, s3, s4, right? And while we start from the basic variable here, yeah, you see that from the first one we have -1, right? The rest becomes 0 except s1. Okay, -1 here, 0, and then s1 is 1, right? The rest is 0. The right hand side is minus 2.5. See, it's minus 2.5. For the second line, the coefficient, the first coefficient becomes 0, and then it's -1, and then coefficient of s1 becomes 0. We have only 1 on s2, right? The rest becomes 0, and then right hand side it's -6. Okay, we put it down here. And for the third one, we have -2, -1, right? -2, -1, and then about 0, 0. S3 is 1, and then S4 is 0, and then right hand side is minus 17. And the fourth conditions is -1, -1, -1, -1, 0, 0, 0, and 1 on S4, and then right hand side is -12. Okay, and for the objective function, it is 20, 16. Okay, and the rest is 0. We don't have slack variable here. All right, so the right hand side also 0. And well, now the condition is, well, we consider three, well, yeah, we select this column, it's 20. Okay, the first one, select row R as the pivot row such that BR is the minimum of BI less than or equal 0. Okay, instead of that column, we look at the row first. Okay, and we select this row because this row has minimum C over -A. Okay, you can follow me, right? Yeah, we select the row first. row. BR is a minimum, BI less than 0. The most negative one. This row is the most negative one. So we select this row. Previously, we select the column first, right? But for dual simplex, we select the row first. Okay. And then we select the column by comparing this value, C over negative A. Okay. We check C and A. Okay. C negative A. So this one, C is 20, right? 20 over negative A is minus 2, then sorry, negative A is 2, right? So it's 20 over 2, right? For this column, it's 16 over negative A is 1, so it's 16 over 1. Okay, with this one is smaller, so we select this column, okay, on this row, so it is this one, x1, right? So x1 will be selected, okay, as our basic variable. Okay, so we use Gauss elimination to make this column to be 0, 0, this row, this element must be 0, 0, and the rest becomes 0 too. Okay, then we transform our table. Okay, again we select from BR which one is the most negative one. We see this row. This row is the most negative one. Okay. Okay. And this column x2 must be entered as our basic variable then. Okay. Now we use a Gauss elimination to make this column, because x2 is now basic variable, so this element must be 0, 0, 0, 0. Okay, only 1 on the x2. Okay. Again, for the next step, next iteration, well, we look at BR first. This B is negative, so well, we select this row. Okay, this row. And which column? Well, we select this column. Okay, because the C over minus A is the minimum. Okay, we select only negative this time, so we select this column. That means, well, our basic variable, well, we introduce S2 as our basic variable, and we remove S4 from the set of active variable. Okay, so we transform this column in order to make this element become 0, 0, 0. Okay, and this element must be 1, this element must be 0. Okay, 0, 0. Okay. Okay, so we obtain this table, and you see that from this table, we don't have negative value of B anymore, right? We don't have no more negative B. That means, well, we cannot further change anything. We cannot further improve our objective function. Okay, so, well, x1 is here, right? X1 is 5, x2 is 7. Okay, just that is our solution, Fishman solution. Okay, so any problem on the dual simplex method?
Hello, Prof.
Yes.
How do you know when you must apply dual simplex method, or can you just apply it when you see a problem?
Yeah, you can use two-phase. You can use
Okay.
two phase if you want. Yeah.
Oh.
But you know that from this one, from this problem, you see it, right? And once you transform it to positive, right? And then you see that the what's it constraint, the relationship is greater or equal. You see that you cannot use the single phase of simplex method, right?
Yes.
What you need the two phase, right? So you have two choices. You can use dual simplex method, or you can use two phase. It's okay.
Okay.
Okay. Vishudha, you have problem? You have any questions?
ยังไม่มีค่ะ
Okay, come. What about others? Sasmita, you well, yeah, take your time to watch a video again, and also well try to do it by yourself. Try to practice. Practice make perfect, you know. Okay, so well, I will what's it? Yeah, I will show you how to use linear programming in Excel. Okay. You have Excel, right? So, well, for example, we have this problem, this maximize minus 3x1 plus x2. Okay, and we have constraint on the minus 2x1 plus x2 lesser or equal 4, 7x1 plus 3x2 greater than or equal 21, x1 lesser or equal 4, and x1, x2 is greater than or equal to 0. Okay, so well, if you want to use Excel, it's very simple. You open Excel and make sure that you install the solver in Excel, right? And from the spreadsheet, yeah. Well, you allocate the cell for your variable. For example, here I allocate C2 for x1, D2 for x2. Okay, and the objective function here, yeah, C4 is an objective function, and I put the formula here. The objective function is what? Minus 3x1 plus x2, right? So the objective function here is formula, yeah, minus 3 times with C2, right? And plus D2, okay? And also we have constraint. For the constraint, of course, constraint, the first constraint is minus 2x1 plus x2 lesser or equal 4. So we put the formula here for the first constraint, lesser or equal 4. Okay, and this is the second constraint. We put the formula here, greater or equal 21, and the last one, it's the third constraint. Yeah, lesser or equal 4. Okay, then while we use solver, okay, we open the solver, and then, well, we set the objective function. Our objective function is C4, right? This cell, C4. And the problem is to maximize, so we select maximize here by changing variable cell. Yeah, we put this cell, these cells, okay, C2D2, right? C2D2, okay. So subject to the constraint, yeah, we put each constraint, this cell lesser or equal this cell, okay. Lesser or equal this cell, and we add each constraint. Okay, and you because all the variables, I mean our decent variables x1, x2 are positive, so yeah, we make unconstrained variables non-negative here. Okay. So wow, because this is linear programming, so we choose simplex linear programming and start solving. Okay, and then we get the report, right? You look at the report, you see that it's the optimum solution found. Okay, so found a solution, that means optimal solution is found. And from the report, you see that you can find the final value. This final value is an optimal objective function, and variable cell. Okay, final value. It is the optimum solution. Okay, our x1, x2. Okay. And also, if we look at the constraint, you see that Excel report the constraint. Well, the first two constraints is binding, and the third one is non-binding. What does it mean? Binding means that that constraint is active. When we say that the constraint is active, that means the solution is on this function. I mean, the lesser or equal turns to equal instead. Okay. And also, this constraint is binding, right? So this constraint is active. That means, our solution is on this line. I mean, 7x1 plus 3x2 equal 21. Okay. Okay. And the third constraint is not active. Okay, because it's this one does not involve in the solution. Okay, the solution is the corner or the intersection between the first and the second function. And if you look at the sensitivity report, you see the first part is a variable cell. The optimal solution remains the same if the coefficient of x1 is in the range of -2 to infinity. Okay, you see that the objective coefficient, the original objective coefficient is -3, right? So allowable increase is 1. That means this value can reduce by 1. Oh, sorry, increase by 1. That means we can change the objective coefficient from -3 to -3 plus 1 without disturbing the solution. Okay, and allowable decrease, that means infinity. That means you can subtract by infinity without disturbing the solution. Okay. So the optimum solution remains the same if the coefficient of x2 is in the range of 1.5 to -1.28. Okay, because we're starting from this objective coefficient, but allowable increase is 0.5. That means we can increase from 1 to 1.5. Okay, and for decrease, it can be 1 subtract by this value. Okay, and for the constraint, the first constraint remain active if the right hand side constraint is in the range of 7 to -6. You see that our original problem, the right hand side is 4, right? But it's 4 here, right? But you see that it can be increased by 3 and decreased by 10. Okay, so it's 4 plus 3, or 4 subtract by 10, 4 minus 10. Okay. Okay, and for the second constraint, you see that the right hand side is 21. Okay, you see that we can decrease by 43, and we can increase by 43 and decrease by 9. Okay. And of course, if we decrease or increase the the right hand side of the problem, it affects the optimum objective function. So we look at the shadow price. That means by increasing the right hand side constraint, we change the objective function by 1.23, yeah, by this value. Okay. Yeah. For example, for this one, you see the objective function changes approximately 1.23, okay, per 1 unit of the right hand side constraint. Okay. And for the second one, you see that because this constraint is active, right? So if we change the right hand side of the constraint, the objective function changes, well, approximately minus 0.07 per unit of the right hand side constraint. Okay. Okay, so yeah. So if we look at the problem, the graphical representation of the problem, you see this is our problem. Okay, and the optimum solution is here, right? Feasible. This is our feasible region. We have 3 constraints, and that these 3 constraints forms this feasible region, and the optimum point is here. And this is direction of our gradient. Yeah, the solid line is the direction of our gradient of the objective function. You see that we move this way. It's well, we increase the value of our objective function. Okay, so you see that, well, when we look at the report, and you see that we can, of course, the coefficient can be increased or decreased, right? Wow, the increasing or decreasing of the coefficient affect the gradient, right? And you see that if it change a little bit in the allowable range, that means, well, the solution that's a change, the solution is at the same, right? But of course, the objective function value is changed, yeah, by changing the coefficient. But we don't have to solve the problem again, right? We don't have to resolve the problem because, yeah, the solution is still the same, right? You just replace it. Well, if you want to calculate the new value of the objective function, you just, yeah, replace it. You just substitute the solution in the new objective function, and it is done. Okay. And in the case of the right hand side, you see that the right hand side, if we change the right hand side, what does it mean? We shift the constraint, right? We shift the constraint. Once we shift the constraint, you see that we change the optimum solution. We change the optimum point. However, we change the optimum point, it does not affect the, well, it affects, of course, but we don't have to resolve the problem, right? Because we can estimate, because, well, you know the gradient, the solution becomes at the same corner, right? If the solution is at the same corner, you can estimate that, well, by changing this right hand side of this constraint, you move the constraint a little bit by changing the right hand side. That means, well, this new constraint is still parallel to the original constraint, right? So you can estimate how it's changed, how the objective function changed, right? That means, well, you can estimate the new objective function. You can calculate the new objective function without resolving the problem. Okay, that is. Any question? Any questions? I think, well, it's better to give you some, well, example so that you can You can practice yourself. Okay, one moment. I'm looking for some problem. Okay, so well, I give you two problems. Well, 3.23, 3.24. Okay. So, well, you should practice on that, well, to solve this problem, these two problems, okay? By using dual, well, simplex method or dual simplex method, whatever you want, you can solve it. And well, from the first equation, Kadim, are you there? Kadim is not here anymore.
Yes, Ajahn, I'm here.
Huh? You're here?
I'm here.
Kadim. All right.
Yes, I'm here.
Oh. Okay. Yeah. I see you now. All right. Sorry. Well, can you tell me? Look at the first problem. Can you solve it using the simplex method?
No, Ajahn,
Why?
because of the third constraint.
Yeah, the third constraint, right? Okay, so if you want to use simplex method, you need two phase, right? Two phase of
Yes.
right. Yeah. Or you can try solving it using the dual simplex method. It's okay. Okay. And for the second problem, yeah, again, the first constraint, yeah, is a problem, right? Mhm. Okay, so wow, you completed these two problems and send me back via email, everyone. Okay, it is an assignment for this week. And we will finish the linear programming. Okay, at this point, and the next week we will move to the next topic. Not any more linear programming. We will deal with non-linear programming from starting from next week. Okay. Is it okay for everyone? So cool.
Then send
Yeah.
it to you by mail.
Yeah,
when
via email.
At the end of this week or today?
Today.
Okay. Okay.
Okay, so you take the rest time to complete this.
Okay.
Mm-hmm.
Today till 12 a.m.
No. Yeah. 4 p.m.
4 p.m. Okay. Right. Only these
Okay.
two, right?
Right.
Yeah. Yeah. Okay. Yeah. Got it.
Okay. Okay. So any question? Any more question from your side?
No, John. Got it.
No. Okay. All right. Okay. Then we finish this class and let you complete the assignment. Okay. Okay. Have a nice day. Bye.
Goodbye, John.